I'm honored to be able to introduce colleague and friend Mark Newman. Mark is professor of physics from the University of Michigan, has a long history with SFI in a variety of capacities over the years, is currently an external professor and member of our science board. Mark, it's a pleasure to welcome you.
Thank you. Hello, everyone. So, as is often the case at these things, this talk will be completely different from the one that came before it. This talk is basically going to be a talk about the theory of complex systems, about how robustness and fragility arise in complex systems. However, though it is a talk about theory, I'm not going to throw a lot of equations at you or anything like that. What I'm interested in here is the ideas. And the ideas all come from work that we've done on networked systems. Systems that can be represented as networks of units joined together somehow. And what it means for a system like that to be robust or conversely fragile. I'm going to start off by just giving a few slides of introduction to the kinds of networks that we solve. I realize that there are many people in this room who are experts in this field, and for them, these first few slides may be rather basic, but I think it's worthwhile going through just so that we're all on the same page. So let me start off by telling you what I mean by a network. As someone who does mathematical physics, I have a very sort of mathematical idea of what a network is. It's a bunch of dots joined together by lines. There it is, that's a network. In the jargon of the field, a dot is called a node or a vertex, and a line is called an edge. And because I've been immersed in this stuff for many years, I will use those words without thinking about them, so you'll need to get used to them. Node for a dot and edge for a line. And why are we interested in these things? Well, we're interested in them because they turn out to be a very useful, simplified mathematical representation of the structure of all sorts of complicated systems that we're interested in the real world. Here is just one example to start us off. This is a picture of the internet. That's the actual internet. It's a network where the nodes are computers and the edges connecting them together are data connections. Cables running through the ground, optical fiber, for instance, running through the ground. This particular picture, which was made by Bill Cheswick, it obviously doesn't show every computer in the internet. There are billions of computers on the internet, and you certainly couldn't cram them all into a picture of this size. So in order to make a reasonable picture, he has grouped together the computers. So probably all the computers at the Santa Fe Institute would be just one node in this network. So they're grouped together. Even so, even though this is a coarse-grained picture of the network, you can immediately see, just by looking at a picture like this, just by eyeballing it, without doing any math or anything, you can see that there's interesting stuff going on here. This network is certainly not completely regular. It's not a square grid or something like that. But it's certainly not completely random either. There's clearly structure in this network. You can see, for instance, that there are these sort of star-like hubs in the network. There are these wheel-like structures. There's this sort of filamentary stuff going on in the background. There's various different levels of things going on here. You don't need to know what those are to realize that those are going to have an effect on the way the system behaves. What is the internet for? The internet is for shipping data around from one computer to the other. That's its role, and one can well imagine that the structure of this network is going to affect how well it does that job. And so that leads us immediately to ask questions about, could I have designed this network differently to do its job better? Or if something goes wrong with this network, if there's a failure somewhere in the network, how robust is it going to be against this failure? I want to make it so that if something fails, it still goes on doing its job. And the answers to questions like that are going to depend crucially on what the structure of this network is. If, to give a stupid counterexample, I constructed the internet so that it was just one big long line, everybody was on the same railway track, and everybody had one stop along the line, then everybody will be connected to everybody else, and in principle you could get a message to anybody you wanted to get it to. But if any one station along the line, any one node failed, it would disconnect the left-hand half of the line from the right-hand half, and this would obviously be a hopelessly badly designed network. So you can certainly come up with bad ways to make networks, and those are the ones we want to avoid. So one of the questions we'll ask is, how can we design networks to do their job in a robust fashion? Let me show a few pictures of other networks that are of interest. So this is an example of a technological network, and as I said in my title, I'll mostly be focusing on technological and social networks in this talk, basically because that's most of what I know about. There are many other interesting kinds of networks. Jen Dunn gave a talk this morning on ecological networks. Sadly, I wasn't here for it, but I've heard good things about it. So there's many interesting examples of networks in biology. However, most of what I'll be talking about is technological and social networks. Here's another example of a technological network, one that many of us are familiar with. This is an airline network. In this network, the nodes are airports, in this case in the United States, and the edges are scheduled airline flights that fly between airports. In this case, scheduled flights of Continental Airlines. Something we notice in this network in common with the previous one is, again, it has hub nodes in the network. It has a few nodes that have a very large number of connections. And in fact, in the airline network, we actually call them hubs. So in the jargon of the field, people refer to these nodes as hubs. In common parlance, we also call them hubs when we're talking about the airline network. We say we flew to a hub airport, and then we fly out of a hub airport again. Those are the nodes that have very many connections, and they turn out to play a crucial role in the functioning of most of these systems. The World Wide Web is another important technological network. People often think of the web and the internet as being the same thing. Common parlance, you know, I found this thing on the internet, I found this thing on the web. They basically mean the same thing. You don't distinguish between those two words, but technically they're very different things. The web is a network in which its nodes are web pages, like this one here. And if you look at a web page, there are things on that page that you can click on, hyperlinks, that take you to another web page. You click on that thing, up pops the other web page. So there is an information connection, a software connection, that connects the first web page over here to this second web page over there. So this is a network of information in which the nodes of the network are the pages, and the edges are the hyperlinks that connect one page to another, that you can click on page A and it will take you to page B. And that's completely different from the internet, which is a physical network of cables running through the ground. The web is a nice example, one of the most famous examples of the application of network theory applies to the web, and that's the Google search engine. It's a splendid example of how you can take a little bit of basic network theory and turn it into $1 gazillion. Because how does Google work? In the old days, when the internet first came along, we had a bunch of search engines called things like Lycos and Alta Vista and stuff, and they were terrible. They were really awful. They did not do a good job. You type something in, and if you're lucky, you might get a page that was something vaguely to do with the thing you were looking for, but most of the time you wouldn't get what you were looking for. And then, in about 1996 or something, along came Google, and it was this revelation, because suddenly you could type things into Google, and it actually came up with something that was useful. How did it do it? Well, the old search engines just looked at the pages. They just looked at what's the text on the page. You know, I type in network theory. It goes look for pages that have the words network theory on them. Google changed that by looking not only at the pages, but by looking at the edges in the network, looking at the links between them. At a very crude level, what it does is it just says, well, pages are important if lots of people link to that page. And what it does is a little bit more complicated than that. But at some level, that's what it's doing. It's just saying, oh, a lot of people made links from their page to this page. A lot of people thought this was an important page. So what Google does is actually interesting. Google does not do a good job of finding web pages. Right? Actually, it does a deliberately crappy job of finding web pages. What it does when you type in something like network theory or something into Google is it goes out and it finds every page it can find that might possibly be dimly relevant to the thing that you're looking for. Right? It deliberately tries to cast a very wide net. That's why when you type in something into Google, it comes back with a page of results. If you look at the top of that page, it has a little label that says, I found 54 million results for your query, or something like that. It's always some huge number that it quotes. There can't possibly be 54 million pages on network theory out there, right? Well, there aren't. What it's doing is it's casting a deliberately wide net in order to make sure that any pages that are relevant are somewhere in that huge set that it finds. What's clever about Google is not the pages it finds. What's clever is the order in which it prints them out. Right? What's clever about it is that the page you're looking for is very often in that first set of 10 pages that comes out when you click the button and do the search, right? It prints them out in a smart order, the most important ones first. And how does it do that? It does it in large part by looking not at the content of the pages, but by looking at the links between them and seeing which ones got pointed to by a lot of people. And just by taking that simple idea, building a web search engine out of it, a couple of guys in California got really rich. I mentioned, so here's just a picture of a portion of the World Wide Web. The World Wide Web is, I should mention, probably the largest network we've studied. Google claims to know about 25 billion web pages. So it's a network with 25 billion nodes. And that's not the half of it. There's a lot of pages out there that they don't know about. So it's a huge network. This is a picture, just a tiny portion of it. The main purpose of this picture is to illustrate that if you've got a really big network, you can't make a picture of it. Right? I mean, this is totally useless, right? You can't tell anything by looking at it. It's just a big hairball. So I did mention biological networks. I'm afraid it's not something I know very much about, but there are a lot of people very excited about biological applications of network theory. This is a picture of a metabolic network. You sometimes see these wall charts. The nodes in this network are metabolites in the cell, chemicals in the cell, and the edges connecting them together are chemical reactions that turn one metabolite into another. And you can represent the cellular machinery, the biochemical machinery in the cell, at this sort of biochemical level by a network of reactions like this. Although I wasn't here for Jennifer's talk this morning, I'm sure she showed many beautiful pictures of food webs of this, which this is one, made by Nia Martinez and Rich Williams. This is a picture in which the nodes represent species in an ecosystem and the edges represent who eats whom for dinner. Since Jen gave a talk about this and I don't know very much about it, I'm going to keep my mouth shut and move quickly on to something I know more about, which is social networks. So to most people these days, if you say the word social network, they're thinking about Facebook and Twitter and so forth, the online manifestation of the social network. But to the people who've studied social networks for the last 70 or 80 years, the word social networks means something quite different. A social network to a sociologist just refers to sort of the mathematical object that is nodes are people and edges are some kind of social connection between people. This idea goes back a long way. The earliest real examples of this came from this gentleman here, Jacob Moreno, who was he was a psychoanalyst by profession, in fact, in this country, in the US. And he pioneered his own form of psychoanalysis, which he called psychodrama. And what it involved was, instead of, getting people to sit on the analyst's couch and asking them about their childhood, instead of that, he got people to interact with one another in groups, and then he just observed their interactions. And the hope was that you can learn something from a psychological point of view by observing people's interactions with one another. And in doing this, he developed these little handy charts, of which this is one. This comes from his 1934 book on the topic. And this one here is a chart that shows patterns of play amongst children in an elementary schoolyard. So this is a hand-drawn example of a social network, very, very early social network. And what you immediately see on looking at a picture like this is that there's two groups. There's a group of triangles over here and a group of circles over here, and it's probably not going to take you a long time to guess that those represent the boys here and the girls here. There's elementary school kids, and the boys and the girls don't play together at all, except for apparently this one pair of kids in the middle here. And it was the ability to see that just by looking, instantly, just by looking at pictures like this, that very rapidly persuaded social scientists that this was a good way of looking at things, and they're still doing it to this day. 80 years later, here's a modern day version of the same thing. So this is data from something called the U.S. National Longitudinal Study of Adolescent Health, or the AdHealth study for short, a large NIH-funded multi-year study. Many millions of dollars went into studying the friendship networks of students in over 100 U.S. junior high and high schools. This is a network from one of those schools. So the nodes represent the kids in the school, and the edges between them represent who's friends with whom. And if you look very carefully, you may not be able to see this from where you're sitting, but if you look very carefully, there are arrows on these edges. They point in one direction. Seems a little bit weird when you think about it. What does that mean, that this friendship goes in one direction? We think of friendship as being a two-way street. Surely it should be a symmetric thing. Well, these arrows here, they are important. They're to do with the way the data are collected. How do you collect data on who's friends with whom? Well, you just go and ask people. You say, so, who are you friends with? And they say, well, I'm friends with him over there. So A says that they're friends with B. What is surprising is that a remarkably large fraction of the time, B does not also say they're friends with A. Actually, in these particular data, about 50% of the time, it goes only one way. So that immediately raises some sort of interesting questions about what's going on there. Some people sort of say, well, the data are defective. There's a problem here. We want to know about the actual friendships, and these data are not getting at them. Somehow we've got to extract the real friendships from these odd directional data. In a recent study I did with one of my graduate students, Brian Ball, we actually took another view on this and said, well, maybe these edges are telling us something. So we went and looked in detail at what's going on with the friendships in these networks where they only go one way. And what we discovered is that in all of the networks from this study, over 100 different schools, you can find a ranking of the students from low to high, such that virtually all, on average 98%, of the edges that only go one way go from a lower-ranked student to a higher-ranked student. In other words, there exists some ordering such that all of the edges are pointing up and none of them are pointing down. We conjectured that this is some sort of indication of social status, that lower-ranked kids want to be friends. They're going to say they are friends with the higher-ranked kids, but the higher-ranked kids are not going to say they're friends with the lower-ranked kids. There is some evidence to support that conjecture. For instance, it turns out that the rankings you deduce from doing this analysis correlate with age, for instance, and it's well accepted that older kids tend to have higher social status in schools. They also correlate with overall popularity. We know how many people nominated you as a friend, and therefore we have a measure of how popular you are. And the more popular kids tend to be higher up in the rankings as well. So there's something to suggest that there's some truth in this. But it's interesting that, this is not a small effect. This is a 98% effect. You can find this ranking where virtually all of the edges go in the upward direction. In other words, it's incredibly rare for a higher-ranked kid to say they are friends with a lower-ranked kid. There's also some other interesting, I don't want to spend too much on it. There's a bunch of other interesting things you find when you look at that. But for instance, it turns out that kids tend to say they're friends with higher-ranked kids, but only a bit higher-ranked, not like a lot higher-ranked. It seems like they want to make it plausible, right? They want to say, oh yeah, I'm friends with this person who's a little bit cooler than me. Because if they say they're friends with the coolest person in the school, nobody's going to believe them. Right? So they say they go just a little bit higher than that. Okay, anyway, so there's some interesting stuff going on there. Here's another interesting example of a social network that comes from a study done by my friend Valdis Krebs. This is from a study of the spread of tuberculosis in an inner city community. So tuberculosis is a disease which many people think of as something that romantic heroines die of in Jane Austen novels, but it's actually become a serious health risk in the last 20 years because of the emergence of antibiotic-resistant strains. And so there's been, again, significant sums of money put into studying the way TB spreads. And one of the reasons that people are interested in studying social networks is because they control the spread of disease. Not just TB in this case, but all diseases spread by contact of people with other people. And so there's some network of who's had contact with whom, and the structure of that network is going to dictate the way the disease spreads. Just as the structure of the internet tells you how information will spread between computers, the structure of the contacts between people dictates the way disease spreads. So like the internet, in this network here, you see that there are some hubs in the network. There are some people that have contact with very many other people. And that turns out to be a dominant effect if you're interested, for example, in the spread of disease. I should point out that not all social networks involve nodes that are just individual people. You can, for instance, have nodes where networks where the nodes represent corporations. This is an example. This is from some work that was done in part at SFI by Woody Powell, Doug White, Jason Owen Smith, and collaborators, in which we're looking at networks of business relationships between corporations. So a node is now a group of people, in effect, not just a single person. That's perfectly fine. You can still use the same kind of social network analysis tricks for networks like this. So that gives you an idea of some of the networks that we're interested in. What I want to spend the bulk of the time here talking about is this idea of robustness and failure in networks. So let's start off by talking about just what do we mean by robustness and failure in networks. So in many of the networks that we're considering, nodes can fail, like the internet, for example. The nodes on the internet are computers. The big computers, sort of in the center of the network, which we call routers, the ones that are responsible for routing traffic from one place to another, those are the ones that you're going to be concerned about if they fail. If my computer, my laptop fails, I'm annoyed, but nobody else really cares. If some big router in San Francisco fails, then, half of the West Coast is going to get pissed off because they can't see the news or they can't send emails to their friends or whatever. So this happens. Nodes, routers fail on the internet. Apparently about 3% of them are down all the time, and yet we don't really notice it. Yet the internet manages to go on. That's because the internet is deliberately engineered to be able to withstand this kind of failure. On the other hand, we can look at it from the other end, and we can think about what happens if we deliberately target nodes for removal. So not just sort of random failure, but we actually deliberately remove nodes from a network. And an example of that comes from the spread of disease that I just mentioned. You can vaccinate individuals in a social network against some disease. Right? We can do the flu vaccine or something like that. And then that doesn't actually remove those nodes from the network. Those people are still there, but they can't catch the flu anymore. And so as far as the disease is concerned, they might as well not be there. We've effectively removed those nodes from the network by vaccinating those people. So that leads us to questions about how many people should we vaccinate and which people should we vaccinate. So there's questions of how can we make a network robust against the failures of its nodes, or we can look at it from the other end and say how can we attack a network to make it not robust, to make it fall apart. An important point to appreciate in discussing this is that when you remove a node from a network, it doesn't just affect that node. If I vaccinate somebody against a disease, sure, it prevents them from getting the disease, but it also stops them from passing the disease on to anybody else. So there could have been other people that they would have infected if they had got the disease. Now that's not going to happen. So you get this knock-on effect. You get a multiplier. For any number of people that you vaccinate, you get a bigger effect for all the people that they would have infected. So some multiplier there. It happens in the case of the internet as well. If a router goes down, sure, that router's off the network now, but it also affects anybody else that router would have passed data onto. So again, there's a sort of multiplier effect. In the epidemiology literature, they call this the herd immunity effect. It means that you don't have to vaccinate everybody in a network to wipe out a disease. You just have to vaccinate enough of them. So given those ideas, here's now a bunch of interesting questions, which I don't know the answer to all of them, but I think they're interesting anyway. So first of all, we can just ask what happens to a network when nodes fail or are removed. It certainly depends on where I remove the nodes, but it's going to change the shape of the network somehow. At the very most basic level, we'd like to understand what happens to the shape of the network when we remove some of the nodes. If we want to talk about robustness or resilience of a network, then we want some way of saying when we've changed the shape of this network if it's robust. If I've changed the shape of this network by removing some nodes, is it still going to function? So I want sort of some measure of functioning of the network, or how good it still is after I've removed these nodes. I want some quantifiable measure of the resilience of the network. Once we have such a measure, then we can go and look at the networks we see in the real world, and we can ask, well, by this measure that I've invented, how resilient actually are they? Are they any good, or are they pretty terrible? Could I make them better? Could I make them worse? Having determined whether particular networks are robust or not, then maybe I can go and look at the robust ones, for example, and find that there are some properties of them that make them robust. Things that I would like to engineer into other networks. I would like to make the internet robust against failure. If I can distinguish particular properties of a network which will achieve that, maybe I can engineer those into the network. So can we design a network to be more resilient? Or, once I know about the things that make a network robust or not, maybe I can design ways to attack a network. When I want to vaccinate nodes in a network, maybe I can design strategies for vaccination that will allow me to effectively attack this network and stop a disease from spreading. So, as I say, I don't have the answers to all of these questions, but what I want to do is tell you about a few case studies that we've done that I think are suggestive, give us an idea about the directions we should be looking in. So first of all, about that measure of robustness. There's various ways you could do it, but here's one simple way of doing it. If you look at most of the networks we're talking about, they have a structure which looks like this. It's divided up into what we call components, i.e. just clumps of nodes. There's a clump of nodes here, and a clump of nodes here, and a clump of nodes here. And usually there is one big clump that fills half of the network, or 90% of the network. It's called the giant component of the network. So the typical structure, and there are good mathematical reasons for believing this to be the case, the typical structure of a network is one big clump and a bunch of other little disconnected clumps around the edge. So now if I'm thinking, for instance, about the internet, the purpose of the internet is to connect me to other people's computers, so I can send emails, so I can read the news, whatever. So now if I find myself in one of these small clumps and I'm here, then I can send and receive messages to the other people in my small clump, but there's only 2 of them. So that's pretty useless. Basically, the internet is useless to me if I can only send messages to the 2 people down the corridor from me and nobody else anywhere in the world. Conversely, if I'm a member of the large clump, the giant component in this picture, then I can send and receive messages from all of these people, which might be 50% of the population of the world or 90% of the population of the world. So a simple measure of what it means to be effective is that this giant component should be large. And a way of quantifying what I mean by robustness in a network is that if I attack this network, or if nodes fail in this network, I still want to have a big giant component. Because it's this giant component here that the network is actually effective for. The people in that component, they still see the network working. The people who've been broken off into the small components around the edge, they see a useless network that doesn't do what it's supposed to do. So if this is my definition of robustness in the network, let me go back to the internet. Here's another picture of the internet. And we have these hubs in the internet. This is a frequent feature of many networks. I pointed out in a few of the others. We have these hubs. There are a few nodes in the network with very many connections. And then there are many nodes that have just a few connections. So my computer just has one cable coming out the back of it. It only has one connection to the internet. But there are plenty of routers out there that have very many connections. There are big switching centers that have cables running to all parts of the world. And it seems clear intuitively that if a node is going to go down, you don't want it to be that one. You don't want it to be the big switching center that's connected all over to everyone. Same thing would be true of an airline network, right? You know, airports go out because of, say, hurricanes. When they do, you don't want it to be LaGuardia, right? You'd rather it was, you know, somewhere in the middle here, some tiny airport that only has one flight a day. I'm not talking about Santa Fe. You maybe think I'm talking about Santa Fe. So the picture is sort of at the theoretical level. Here's the picture. I take some network. If I remove nodes at random, they just fail at random, then because most of the nodes in the network are not the hubs, most of them are just the ones that have one or two connections, then most likely the ones that are going to fail are going to be the ones that just have one or two connections. They're going to be these sort of peripheral ones that are not very well connected, because that's almost all of the nodes. That's 99% of them. So if I'm just hitting things at random, 99% chance I hit those. And I can remove those from the network, and then what you get is this. Well, those nodes have gone. Indeed, they no longer work, but the rest of the network is pretty much just fine. Okay? Conversely, if I deliberately target the nodes that have the largest number of connections, same number of nodes being removed here, but it has a really devastating effect on the network because they were the big hubs, the big switching centers that connects everyone to everyone else. So this is a good news, bad news story, right? In some cases, we want this situation. In the internet, we're mostly concerned about random failure. This is a good thing. The network is going to be quite robust. In the case of vaccination, we want to do this kind of thing, where we target deliberately the nodes that are going to be most effective at tearing the network apart and stopping disease from spreading. So here's an example of a simple theoretical calculation we did for, these are not for real networks, they're now for fake networks generated on our computers. But what we're doing here, look at this top plot here. What we're doing here is we're removing nodes, and we're removing the most connected nodes first, the ones with the largest number of connections. In the jargon, we call it the degree of the node. So it's the ones with the highest degree, where your degree is how many connections you have. So we're removing those nodes, and we're plotting the size of the remaining giant component as a function of the number of nodes we removed. And what you see is, as we remove just a few % of the nodes, the size of the giant component comes down. It was initially 0.6 something. It was 65% of the network in the giant component. Pretty effective network. It's working pretty well, but it comes down very sharply. And by the time we've removed only about 2.5% of the nodes in the network, the giant component is completely gone. It doesn't exist at all. So by our simple measure of what we mean by robustness, this network has now been totally destroyed. Nobody in this network is connected to anybody else. So if this were a vaccination strategy, it would be an extremely effective vaccination strategy. We'd only have to vaccinate 2% of the people in the network, and we would have prevented the disease from spreading. There would be no giant clump for it to spread in anymore. There would only be disconnected little clumps. So this is, you know, this is a nice idea. This is an idea that's been around for a while, but it has some problems. And one of the problems is, how would you put this into practice? How would you find the people that have the very large numbers of connections? Because we don't have a map of most social networks. Maybe we have, at great expense, gone out and made a map of a few high schools around the country. But in general, we don't have a map of the social network of the world as a whole. We'd like to find the hubs in the social network so that we can vaccinate them. Pretty much what we do at present is we vaccinate people at random. You know, pretty much when you're giving out flu vaccine, you just give it to whoever walks into Walgreens and says, I want a flu vaccine. Right? In fact, in some cases, we are doing precisely the wrong thing in public health terms. For instance, we tend to vaccinate old people. There's a good reason for that. Old people are the ones who are going to be at risk if they get the flu. But from a public health point of view, it's the wrong thing to do because old people, on average, have a lot fewer contacts than people who are younger than them. And so they're definitely not the hubs in the network. They're not the people who are going to pass on the disease to other people. And so you're not getting that knock-on effect, the herd immunity effect. What you want to do is find the people who have a lot of connections. So here's one clever suggestion about how you should find the people that have a lot of connections. This was a suggestion made by Reuven Cohen and Shlomo Havlin a few years ago. They call it acquaintance immunization. They say you should not immunize people chosen at random, which is basically what we do at the moment. Instead, you should choose people at random, and then you should ask them to nominate one of their friends. Then you go find that friend and you vaccinate them. So this sounds like a crazy idea, right? But actually it's not. Actually it's a very clever idea. Why? Because somebody who has 1,000 friends has 1,000 chances to get nominated by any of them. So they're much more likely to get nominated than the person who only has one friend. This is automatically going to single out the people who have a lot of connections to get vaccinated. As far as I know, this strategy has never actually been put into practice. They simulate it on a computer, and it appears to be quite effective. There obviously would be, some sociological issues to contend with if you wanted to actually do this in practice. However, this is not the whole story. I should point out that, to go back to this picture from the TB study, there is another aspect to this. So it is important to remove the hubs if you just want to prevent the disease from spreading. But the hubs actually, in this case, have even more importance than you might think they have. Why? Well, so the hubs are nodes that have high degree. That is, they have high number of connections. And if you wanted to know what is the property of the network that makes the disease spread or not, what change do I have to make to it to stop the disease from spreading, a reasonable guess might be that the crucial property is the average number of connections a person has, the average degree in the network. If I can make the average number of connections lower, then there's just, there's fewer connections in the network, and it's going to be harder for the disease to spread. So if I were going to make a mathematical theory of it, I might guess that that was sort of the numerical quantity I wanted to focus on. Well, it turns out that that's the right general idea, but it's not exactly correct. It turns out that the correct answer is not that you should look at the average degree, but that you should look at the average of the square of the degree. That turns out to be the crucial property, and I'll tell you why. So the hand-wavy argument is to take a look at this picture here. So there are hubs in this network. There are people with high degree, like this person in the middle there. And if that person got sick with TB, then that would be very bad. They could give the disease to a lot of other people. But the crucial thing to notice is that this person can also catch the disease from a lot of other people. Right? If this person has 100 friends, then there's 100 people they can catch it from and 100 people they can give it to. So they're 100 times 100, 10,000 times more effective at spreading the disease than the person who only has one friend. So it turns out to be the square of your degree, the square of the number of connections you have, not just the degree itself, that's the important parameter. So that means that somebody with 1,000 connections, a degree 1,000, is 1,000,000 times more efficacious at spreading the disease than somebody who only has one. So it's a huge effect. And this means that the hubs in the network are even more important than you might otherwise think them to be. They really have an enormous outsized effect on the spread of disease. Here's a real practical example of that. This comes from data collated by Steve Borgatti. And it describes the spread of SARS, severe acute respiratory syndrome. I don't know if you remember this from about 10 years ago. This is a sometimes fatal form of viral pneumonia caused by coronavirus. There was a big outbreak of it in Southeast Asia in 2002, 2003. And the data that Steve looked at in this figure here come from the outbreak they had in Singapore. They had particularly good surveillance data in Singapore. And what this shows is the progression of the disease through the cases that they know about, starting from the first case they know about over here, case number 1. And what you see is case number 1 here was a hub. They were somebody who had a lot of connections and they passed the disease on to many other people. That's not true of most people in the network. Unfortunately, it was true of person number 1 there. But it's not true of most people in the network. Most of the people that number 1 passed it to were just ordinary Joe. Only had a few connections, and so didn't pass the disease on to anybody else. So maybe passed it on to 1 or 2 other people. But pretty much the disease would have died out at that point if it weren't for the fact that one of the people that person 1 passed it on to was person 6, who was another hub. Gave the disease another big boost, right? But again, most of the people 6 passes it on to, they're just average Joe. They don't pass it on to anybody else. Again, the disease would have died out at that point, except that 6 passes it on to 35, another hub, and so forth. So what you can see in this picture, so these are real data of an actual outbreak. You can see that it is the hubs that are single-handedly keeping the disease alive. If you took out just those few nodes in the network, then the disease would not spread. And that's really the goal of these targeted vaccination strategies. If we can find these few people who are responsible for most of the spread of the disease, then by vaccinating only a tiny fraction of the community, we can get a very large herd immunity effect. In principle, you should be able to vaccinate only a small percentage and be able to wipe the disease out entirely. So, having said that, I want to, in the last few minutes, talk about some other properties of networks which I think are sort of interesting and suggestive, turn out to have an effect on resilience. So at this stage, we're sort of at the stage of we're looking at networks, we're seeing interesting structural properties, and then we look at their robustness, and we say, oh, this one's robust, or this one isn't. Perhaps it's associated with that property. So this is a very sort of empirical, experimental way of doing this. We don't really know the exact answers to these questions at the moment. So what we're doing is we're looking out there at the networks we see and asking which ones are robust. Perhaps by looking at those ones, we can learn something about what it takes to engineer a robust network. So one thing that we've looked at is the phenomenon of assortative mixing, a homophily. This is something that you see a lot in social networks. Homophily is the tendency for people to associate with other people that they perceive as being similar to themselves in some way. So you'll find that young people associate with other young people and old people associate with other old people. That's homophily by age. You'll find that rich people associate with other rich people and poor people associate with other poor people. That's homophily by income. You find homophily by age, income, race, nationality, what language you speak, educational level. Pretty much you name it, people associate according to that. People just like to associate with other people who are like them in some ways. There are rare examples of the opposite effect, which you might think they would call heterophily, but they actually don't call that. It's usually called dissociative mixing, in which people associate with unlike people, and the primary example of that is dissociative mixing by gender, when we're talking about, for example, networks of who's dated whom. Most dating connections are between people of opposite gender. And so you have a dissociative effect in that case. However, primarily what you get is networks where similar people tend to associate with one another. Here's a few little snapshots just to try and persuade you of that. This is from the Ad Health study again. This is a scatter plot of friendships amongst kids in one of the schools in that study. So each dot here represents a friendship between two kids, and the ages of the kids are represented along the two axes. So this dot here represents a friendship between a 10th grade kid and an 11th grade kid, for instance. And what you see looking at this picture, you can just see that there is a higher density of dots along the diagonal and a lower density off the diagonal. That indicates that a majority of friendships are between kids of similar ages. Here's another example. This is marriages in the US from the US National Study of Family Growth, study conducted in the 90s at the University of Michigan. It shows the age at first marriage of husbands and wives in the study. So each dot is a couple, and this is the age of the husband, and this is the age of the wife. And again, you see that there's sort of a band along the diagonal indicating that people are marrying people of roughly the same age as them. Now, I'm not claiming that who's married to whom is actually a network. Surely it isn't. I imagine people are only married to one person at a time. So there's, no actual network there. But I'm thinking of marriage as being a proxy for people being friends. I'm assuming that people are friends before they get married. So this may be some indication that people are friends with other people who are about the same age as them. Actually, this plot is kind of interesting. I just think from a sociological point of view, I find this plot quite interesting. You'll notice that this is totally irrelevant to the topic of this talk. All the dots around here, right? I mean, everybody's getting married apparently at age 18. My friends, we all got married in our 30s, which means that we're all here. This is where me and all my friends are, in this completely empty box up there. All my friends are university professors. This tells me that university professors are not normal people. Right? Here's the population of the US. Here's me and all my friends. Okay, let me move along here. So what I actually wanted to the relevant topic here is this. So now here's an interesting twist on this. So assortativity or homophily is people associating with other people who are similar to themselves. What if I now do this according to degree? Remember, degree is how many friends you have. It's the number of connections you have. So assortative mixing by degree is people with lots of friends tend to hang out with other people who have lots of friends. So the gregarious people are hanging out with the other gregarious people, and the hermits are hanging out with the hermits. Or you could have the reverse, disassortative mixing, which would be the party people are hanging out with the hermits and vice versa. This is from one of the earlier studies of this phenomenon by Sergei Maslov. This is a very nice, colorful plot that purports to show this phenomenon I'm talking about. But actually, I find it very difficult to interpret that plot. So I'm going to move quickly along to this alternative representation, which I find easier to understand. This is actually for internet data. So what this shows is, for the internet, horizontal axis is degree, i.e. how many connections does a node have on the internet. Vertical axis is what's the average number of connections that the neighbor of that node has. Okay? So I'm a node that has degree 10, say. My neighbors, on average, have degree about 200 or something. That's what this is telling you. So as a function of my degree, my number of connections, how many connections do my neighbors have? So you notice that the curve goes down here. What that's telling you is if I have few connections, my neighbors have lots. And if I have lots of connections, my neighbors have few. So the internet is disassortative by degree. The party people are hanging out with the hermits in the internet. I mean, it's not people, it's routers, computers, but you get the idea. So now I can ask, what do assortative networks and disassortative networks look like in this particular case of assortativity by degree? If I have assortativity by degree, that means all the party people know each other and all sticking together. That tends to give you a big sort of dense clump in the middle of the network where all the highest degree nodes are all stuck together. You see that here. And then all the low degree nodes form this sort of halo around them. Conversely, in the disassortative case, you tend to get these stir-like structures. Here's a party person hanging out with a bunch of hermits. Right? So you tend to get this star and this star and this star like that. So the high degree nodes don't want to be near each other. They tend to repel each other, and they like to hang out with the people who only have one or two connections. So you can actually eyeball networks like this, and you can very easily, after you've seen a few of these things, you can very easily tell the difference between this assortative and disassortative.
Mark, wouldn't that just be a reversion to the mean effect? If I'm a party person, most of the people in the community have fewer connections than I do.
So that's certainly true, and when you do the statistics of that, you have to allow for that. So we have to ask, is what we're seeing more than we would expect just because of reversion from the mean? We do know how to account for that in the statistics, so we can say whether what we're seeing is just the basis of just what we'd expect on the basis of chance, or whether it's actually an even bigger effect than that. But you're absolutely right, that is an effect, and you have to account for that.
So you're finding that it is an even bigger effect?
Right. So we find an interesting pattern. We find that social networks essentially all fall into this category. Statistically significantly, they are assortatively mixed, that the party people are hanging out with other party people. And virtually all other kinds of networks fall into this category, including the internet, the World Wide Web, biological networks of various kinds. So we see both of these types of networks in the real world, and it's mostly social networks on this side and other networks on that side. And those results are statistically significant in that sense. So now, let me ask about the robustness of these networks. So what I'm going to do now is, again, I'm going to try and vaccinate these networks by removing the most connected nodes from them. And what I found is, so this R here is a number that represents assortativity at the top. Negative numbers represent disassortativity. So I have a scale of assortativity here. And what I find is that the assortative networks, that's this curve here, are relatively robust. I have to remove a lot of nodes before I get the giant components to go away and the network falls apart. If I'm going to vaccinate this network to stop the spread of disease, I have to do quite a lot of work, vaccinate quite a lot of people. The disassortative case, as this one here, is exactly the reverse. It's a very fragile network. I hardly have to remove any nodes before everything's gone and the network completely falls apart. This is actually kind of not what I would hope to see. Because remember, these are the social networks, so things that diseases spread over. I would like them to be vulnerable to vaccination. But they're not. They're the assortative ones. They're the ones that are particularly robust. These are things like the internet, technological networks. I want that to be robust. Unfortunately, it isn't. Those are the ones that are vulnerable. So this is not an entirely happy picture. Things are kind of the wrong way around here. But certainly this is one suggestion. So one way we see of robustness arising in networks is through this assortativity or homophily by degree. And you can sort of see why that would be. Why would this be robust? Well, if I'm going to take away the highest degree nodes in the network, the thing with this network is that all the highest degree nodes are all clumped together in the middle there. They're all sticking to each other. So you take them out, you're going to make a hole in the middle of the network, but you're pretty much going to leave the whole of the rest of the network as it is. You're kind of focusing all your attack on one small region in the middle of the network, which is not a very efficient way of doing it. Conversely, over here, the high degree nodes are very well spaced out because they don't want to be stuck together. So that spreads out your attack much more evenly over the network, and it's a much more efficient way of doing it. Here's another interesting property that seems to have an effect on robustness in networks. Transitivity, in mathematics, transitivity is sort of like if A equals B and B equals C, then A equals C, that kind of thing. In social networks, transitivity is sort of the equivalent thing. It's if A knows B and B knows C, then A knows C. In other words, the friend of my friend is also my friend. That's the transitivity effect in networks. Another way of saying that is that we expect to see lots of triangles in networks. If it's really true that the friend of my friend is also my friend, then the three of us form a triangle. Well, it turns out that this is a significant effect, particularly in social networks, that you see a lot of triangles because of this kind of friend of a friend effect. So then we can ask, oh, we've seen this property of networks. Let's go and investigate whether that imparts robustness on the network or not. So again, this sort of this empirical approach of we're trying to find out the things that make a network robust. So I'll skip this one. Here's this is a slightly complicated plot, so let me walk you through this one. It's all calibrated in technical terms here, but this occupation probability here basically it's basically how many people am I vaccinating, except that it's the wrong way round. Here's I've vaccinated nobody, and I'm vaccinating more people as I go that way along the plot. That's just the way it's done in this calculation. But anyway, so this over here, this point here, represents I'm vaccinating nobody. No, ignore this stuff over here. This means I'm vaccinating nobody. I'm vaccinating more people as I go this way. And the vertical axis is size of the giant components, this measure of how robust the network is. So first of all, this thing here, C, this clustering coefficient, is a measure of how many triangles there are in the network. If it's 0, there's no triangles. If it's large, there are many triangles. So first of all, what you see is if there's no transitivity in the network, then the size of the giant component actually starts off bigger than if there are a lot of triangles in the network. Why is that? Well, it's because we have to be careful in this calculation to compare apples to apples. We want to compare networks that are the same size and have the same number of edges. Now, if you introduce a lot of triangles into a network, but you keep the same number of edges, what it means is you end up wasting a bunch of edges. See, there's a connection to me and there's a connection from the friend of my friend, and now I'm going to add an extra edge between me and that person. I'm going to complete the triangle and say the friend of my friend is also my friend. Well, in a way, that's a wasted edge. I didn't need to put that edge in there because I already had a connection to that person via another path. So there are a bunch of redundant edges once you start introducing triangles, and that means that you weren't able to get such a large giant component. You weren't able to get such a robust network because you had basically wasted some edges doing other things. But now an interesting thing happens. We start removing nodes from the network, and what you see is, well, the size of the giant component goes down, of course, but at some point these curves cross over, and the ones with more triangles start doing better, and the ones with fewer triangles start doing worse, and that's for exactly the same reason. Those redundant edges are now helping you. Once you start removing things from the network, it's good to have redundant paths in the network, because that gets you other ways to connect to the people that you wouldn't otherwise be connected to. So this is an indication that transitivity is a good thing in networks because it introduces redundancy in your connections. So it's good over here. It's good when a lot of things are expected to fail, but it's bad over here because in order to do it, you have to commit a lot of extra resources to your network, create a lot of extra edges that weren't really necessary. So whether it's a good thing to do depends on whether you seriously think there's going to be a lot of failure in your network or not. So you might want to regulate the amount of transitivity depending on your prediction of how much is going to fail in the network. So I'm almost out of time here. Let me just, here's one sort of more speculative thing to finish off with. This picture here comes from a study that I did with a marine biologist called David Luceau. who studies the social networks of animals, and in this particular case, it was dolphins. So David spent 7 years bobbing around on boats in Doubtful Sound, New Zealand, watching dolphins. And dolphins, it turns out, I didn't know this, have a very active social life. They make friends. You can determine their social networks by their behaviors. And David became very good at this and made social networks of a number of different communities of dolphins during his studies. This is one of them. This one is particularly interesting because during the period he was studying this community of dolphins, one of the dolphins, the one represented by that yellow triangle in the middle there, disappeared. Don't know where it went. Wasn't dead because it came back 2 years later, but it disappeared for 2 years. And when it did, this community split up into two different communities. This half and that half went their separate ways and stopped talking to each other. Apparently that one dolphin in the middle was the glue holding the whole thing together, and when it was gone, everybody split apart. Another way of saying that is, well, you can see this pretty clearly, in fact, just by looking at the network. There's sort of a bottleneck here. There's a dense clump of connections here, and there's a dense clump of connections here, but there's a sort of bottleneck. There's a cut here where I wouldn't have to cut very many in order to separate these things into two halves. One of the things that in the stuff that I've been showing you is, what we've seen is that we can attack networks. If we want to vaccinate, for instance, we can attack a network by looking at the high-degree nodes, but the high-degree nodes might be scattered all over the network. This is suggesting another strategy, that we should focus our attacks on certain areas. Here's a weak point in the network. Let's expend a lot of our resources in our attacking on just cutting through that one weak point so we can sever the network into disconnected parts, and then the disease or whatever it is won't be able to connect between the parts. That's a completely different idea of attacking the network from the idea of spreading our attacks around all over, just looking for high-degree nodes, and everywhere we see a high-degree node, let's take that node out. So this is a completely different approach. It's one we're thinking about a bit now, but it turns out to be one that is computationally hard to tackle. But it's a suggestive idea that maybe there's another completely different alternative to attacking networks that we haven't considered here. I did want to leave a little bit of time for questions, so I had a few open questions here which I'll just stick up on this slide, but otherwise I am going to stop talking. Thanks for your attention. I'd be happy to answer questions if you have them.
Questions, please? Yes. Because we've got the AC on, please speak in directly into the microphone.
You talked about social networks and engineered networks. And it seems to me that you mixed up two different things, because in the internet, when you take a node out, in order for it to function, it needs another path. It needs to work around the outage. Whereas in the disease, the infection stopping networks, the network is still a connection between people, and they still function, but the disease can't get through that inoculated node. And this came up again at the end when we were talking about the bottlenecks, because in networks like the internet, it's not the triangles that they engineer redundancy in, but across those bottlenecks, so that you have a higher degree of nodes that you have to take out in order to break the connectivity between the parts. And so I was hoping you could shed some light on the fact that you seem to be using the same kind of mathematical analysis between networks that are designed to have redundant paths and ones that aren't.
Okay, thank you. So that's an excellent question. So you're right, I am sort of using the same kind of mathematical analysis, but I think that the answer is that I'm sort of making my analogy in a different way. So in the case of the internet, you say, yeah, the interesting quantity, people want this network to work. They're trying to send data. So from the point of view of the people, it's like a question of having a path to your target. And if this node goes out, I'm going to have to route around it. So a robust network is one that's going to have several different paths from each source to each target, and so forth. And then you say in the case of the vaccination network, well, you can vaccinate people, but the people still just work fine. But the analogy I'm making is not to look at it from the point of view of the people in the vaccination version, but to look at it from the point of view of the disease. So now imagine that you're the disease. You've had a path taken away because this person has been vaccinated. Your goal now is to find another path to route around that so you can still infect the other person. Now, of course, our goals as human beings are diametrically opposite in these two cases. In the case of the internet, we want there to be a path. We want to make the network robust. We don't want it to fail under the failure of its nodes. Whereas in the case of the disease, we want to find ways of attacking the network so that we can stop these connections. But if you look at if you look at the analogy where you equate the spread of the data with the spread of the disease in the vaccination network, then mathematically, although we're interested in opposite questions,
Good morning, everyone. I'm Chris Wood, Director of the SFI Business Network, and on behalf of the entire Institute, it's my pleasure to welcome all of you here this morning for the beginning of the scientific sessions of our Trustees and Business Network Symposium on Resilience. I'd like to begin this morning, as I did last night, by acknowledging that our focus today is going to be on the science of resilience in all its aspects, from a wide variety of different perspectives, from disaster management through ecology, through computer networks, and many others. But while we're doing this, I think it's essential that we continue to be mindful of the consequences of last week's storm on the East Coast. We have people here who made it out of the East Coast. Fortunately, we're very happy to have you here. But there's still people who are very, very deeply and personally affected by the storm. People were killed. People were injured. There are people sitting in lower Manhattan eating crackers in dark rooms on high floors of buildings they can't get out of. So let's keep our minds on the science, but let's not forget the extreme human tragedy that disasters like Sandy present to us. It's now my pleasure to introduce my friend and colleague, Doug Irwin. Doug is professor at the Santa Fe Institute, senior scientist at the Smithsonian, and chair of the faculty at the Santa Fe Institute. And Doug will introduce our postdoc presentation this morning. Doug?
Thanks, Chris. So when I took over as chair of the faculty about a year and a half ago, one of the things I learned was that our excellent crop of postdocs felt a little bit left out of things. So to their annoyance, I came up with a way of including them. So what we like to do is a way of introducing the postdocs to the members of the Business Network and the other people here today is go through a set of brief introductions. This is an opportunity also for the postdocs to practice the proverbial elevator speech. Each of them has 2 minutes to introduce themselves and the research to you. And we hope that this will facilitate interactions today and tomorrow during the rest of the meeting. We'll do this in 2 parts with one group this morning and then another group immediately after lunch as a way of encouraging all of you to come back promptly from lunchtime activities. So, Cleo.
My name is Cleo Andrus, and my big question at SFI is how do our personal relationships shape the world? So how do I answer this question? I look at big online data such as social networks, telephone calls, political data, migration, and flights. And what I do is I get our old software that represents the world, our GIS software, Geographic Information Systems, to cooperate with these social data sets. And the way I do this is I output a measure that I call social distance, which takes into account both Euclidean distance, travel time, and our social relationships with people. So this means that places are connected through humans, through our ideas, through our conversations, and not just roads. And how does this result? In the macro sense, it results in a lot of flights from, for example, Boston to San Francisco, because there are a lot of relationships between those places. In the micro sense, it relates to us valuing place differently. For example, a Yogi Berra quotation, "Nobody goes there anymore, it's too crowded." This quotation means that he's valuing places based on his relationships. Thank you very much.
Excellent. Charles.
Yeah. I don't look like that. Hello, good morning. My name is Charles Perot. I'm an archaeologist interested in human evolution. And as a field archaeologist, I work in Northeast Asia, so Tibet and Mongolia. Tibet is the largest high elevation ecosystem on the planet and one of the harshest habitats in the world. And one of the questions I'm interested in is when and why did humans at some point in time decided to go live up there? And this question is part of a larger research endeavor in which I'm trying to explain why humans, with the physical endowments of a tropical ape, have come to dominate so many of the Earth's ecosystems and so rapidly. So a few thousand years after humans leave Africa, they're closing in on the Arctic Circle. And my working hypothesis is that one of the key processes by which we adapt to new ecosystems is cultural evolution. That is, through the evolution of the information that we socially transmit from each other. So I'm interested in the origin of this capacity for cultural transmission.